welcome to GEMCHEM. Now today's video is on stereochemistry part 4 video, and here we are going to deal with symmetry operations and elements. Now before starting, already 3 videos of stereochemistry is being uploaded in the channel. You can watch it. I will give the link in the description box as well as the I button present above this video. Now if you are new to GEMCHEM, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. Now first of all, symmetry operation means that these operations are present in a molecule in such a way that on performing these operations we will get back the same molecule in same substituents placed in same places. So right now we will start. So see this one. Certain operations such as rotation, that is if we try to rotate the molecule, or reflection, that is using a mirror if we try to see its image, these operations are being performed, and if by so doing an arrangement is obtained which is identical or indistinguishable from the original one, that is it is superimposable on that original molecule, then the operation is called symmetry operation, and the molecule is said to possess an element of symmetry defined by the operation performed. So this element of symmetry will be defined by rotation or reflection, or maybe sometimes both together. So symmetries based solely on simple rotation is often called symmetry of first kind. Similarly, whereas if we see in the last line, the symmetry based on reflection or rotation reflection is known as symmetry of second kind. And in next few slides we are going to deal with the details of it. Now, it is customary to describe the symmetry of a molecule in terms of 4 symmetry operations and 4 corresponding elements of symmetry. Now, what are these 4? We will see one by one. Now, first is the simple or proper axis of symmetry. Here, we are going to rotate the molecule in such a way that it will be a rotation 360 degree by n. That is, we are rotating the molecule around an appropriate imaginary axis by an angle of 360 degree by n. And we arrive at an arrangement which is indistinguishable from the original one. And the axis is called as n-fold simple or proper axis of symmetry. And the degree by which it is rotated, from there we can see and get the n value, and from that n value we are naming the axis as Cn. So suppose if you are rotating a molecule by 180 degree, so it will be 360 degree by 180 degree, and we are getting a value of 2. So the axis will be known as C2 axis, and the operation will be known as C2 operation or Cn operation in case of n value. Now the operation is repeated n times, leading to the orientation identical with the original. Now this will be more clear if we go to the examples. So let us see. Now first you can see this is a water molecule, right? Now remember, if suppose we see this is the water. Okay. Now if we just rotate this axis, that is this is the axis taken passing through the oxygen, and we just rotate the molecule by 180 degree. Until we are marking this A and B, we will not be able to distinguish whether there is any change or not. So after 180 degree rotation, it will be like this, right? But in actual case, the nature is not marking A or B, right? So when we rotate by 180 degree, it will be an identical structure. So right now we can understand that it possesses an axis of symmetry which is known as twofold axis of symmetry, and since it is being rotated by 180 degree, so 360 degree by 180 degree gives us 2. So this is a twofold axis and represented by C2. So this molecule possesses a C2 on rotation by 180 degree. Now if we go for the next one, see here, this is a chloroform and it is tetrahedral in structure. So we have already seen how methane looks, just like that. So here we are rotating the molecule about this axis. So this is our axis and we are rotating it by an angle of 120 degree. Why? Because all these substituents have a gap of 120 degree. So once we rotate by 120 degree, then this chlorine will come here. This particular chlorine will go here and this chlorine will come here. But the structure will be same as the previous one. That is, this will be like this only. Chlorine, chlorine, chlorine. And here will be H. So no difference, right? So we cannot distinguish between these two. So this has one C3 axis because 360 degree by 120 degree gives us 3. So this is one C3 axis. The same axis is present for ammonia as well as NR3. Now let us see about the ammonia part. If we consider for ammonia, ammonia looks like this. N, H, H and here a H. And here is a lone pair. So it looks like this, and on being rotated by 120 degree around this axis, then this comes here. Suppose this comes here and this goes here. So no change in the structure. Similarly, if we substitute each hydrogen by R, then same thing, right? So it possesses one C3. Now if we go for benzene, let us see for benzene. So benzene here, its structure is like this. Now if we consider an axis coming from here and down here, okay, so it is present in the plane. This part is towards us, okay, and the back part, that is the red part, will be outside the plane, that is below the plane. This is towards us, orange part, and red is away from us. So this is a 3D structure, right? So if we rotate it by 60 degree, then what happens? Simple, this point comes here, this point goes here, this point goes here, whereas this point comes here and this point goes here. And ultimately we are going to get this structure only, right? So no distinguishing can be done between these two. So it possesses a 360 degree by 60 degree, that is 6 C6 axis. And again, for another consideration, if we see, if the benzene ring is like this, as we have seen, other axes are also possible. This is towards us. So the other axes are C2 axis. If we consider an axis passing through this and we rotate it by 180 degree, okay, so what will happen? This point will come here, this point will come here, this will remain intact, this will remain intact, whereas this point will go here and this point will go here. Similarly, same thing can be done if an axis passes through here and axis passes through here by a rotation of 180 degree. So there are total 3 C2 axes passing through the vertex. Again, if we see in greater clarity, then we can see this benzene ring. If we consider this benzene ring can have a C2 axis passing through the bonds, and again it has 3 C2 axes from here. So what we get finally is that this one, see here is one 60 degree axis and others are 180 degree. So benzene has 1 C6 perpendicular to the plane of the molecule and 6 C2 lying in the molecular plane, 3 passing through the opposite atoms and 3 bisecting the opposite carbon-carbon bonds. Now another one, if we see this one, see here on 180 degree rotation, this methyl goes here, this methyl comes here, whereas this hydrogen comes here and this particular hydrogen goes there. So it possesses one C2 axis. This is cis 1,3-dimethyl cyclobutane. For the next part, if we try to rotate from this way, that is, if we consider this axis present here, then this will go here and this carbon will come here, and ultimately same identical structure will not be obtained. So here there is a change. What is the change? If we see here, the axis is passing through the opposite sides here in this way. So we just rotate it by 180 degrees. So this methyl will come down and this methyl will go up. Lots of imagination are required during this process. So try to see this. This methyl will go down, whereas this methyl will come up by 180 degree rotation. So this molecule also contains one C2 axis. If we see for this one, trans dichloroethylene, this axis is like perpendicular to the molecular plane. So this is the molecular plane. This axis is perpendicular to the molecular plane. So if we rotate it, we will get chlorine here and this chlorine goes there. So see, this is the plane given and in that plane there is C. Here is our hydrogen. Here is our chlorine, here is chlorine and here is hydrogen, right? Now here is an axis present and if we rotate by 180 degree, this chlorine comes here, this chlorine goes here and ultimately we get one C2 axis. For next one, let us see. Now in this case we are getting a cyclopropane ring. So cyclopropane ring has 120 degree rotation when placed here. That is this one. This is placed in the plane. So if we put an axis here coming from here and this is 120 degree rotation. So there will be three positions similar and three C2s. Where are the C2s present? It is present here, passing through this point, then this point and ultimately this point. So three C2s are present, right? Now we are going to deal with linear molecules. Now in the linear molecules there is a important axis, that is this possesses a C infinity axis. On infinite degree of rotation there will be always similar configurations and also it possesses a C2 passing through this bond and passing perpendicular it. So acetylene contains one C infinity axis coincident with internuclear axis since rotation around it by an angle given is infinity, right? An equivalent structure. Infinite C2s are present here also. Many C2s can be present and this one, that is HCN, has no C2 axes because H and N is different and it has only one C infinity axis. Now we are going to deal with our second thing, but before going to the second thing, it is customary to understand that if suppose there is a C2 as well as C infinity, so which one will be our principal axis? The axis which contains the highest order is known as the principal axis. So here C infinity will be our principal axis. In case where a molecule has several symmetry axes of the same order, the one passing through the greatest number of atoms is taken as principal axis. Okay. Now if we see for this one, naphthalene, then here a C2 passes. On 180 degree rotation we will get same thing. Similarly for here also. Ethylene molecule, it has one C2 axis. Now we know one thing, it is a new topic, that is allenes. These kind of moieties are known as allenes. Now if you consider here this part, then remember these two hydrogens are in plane with these double bonds, whereas this hydrogen is below the plane and this hydrogen is above the plane, and we will mark it as D, C, B, A. Okay, and we are going to see what are the axes passing through these. Remember, there will be three C2 axes passing through it. How can we understand it? It is easy to understand, but concept of Newman projection is important. Right now, if you don't know about the Newman projection, you can see the video on it. I will give the link in the description box as well as the I button present above this video. So one C2 axis passes through this. this on 180-degree rotation will give same thing. Okay, and another C2 axis passes through this point, that is passing through this here and going through this. Here will be one C2, another C2 will be here. Now how can we understand that here will be C2s? This can be understood by projection. So first we need to draw this one. So this is our carbon, right? And we see that if we see from here, then HB is present in this side, I's here, okay, keep I's here, and here is our HA, and this will be now in the top, that is HC will be in the top, clear? So HC is written as in the top HC, in the down portion there will be HD, clear? Now there is two C2 axes. Where it is passing through? Here. It is passing through here, C2. Similarly, what will happen on doing the C2? This will come here and this will come, this D will come here. So ultimately same configurations will be obtained. Another C2 is present in this side. So this is also C2. So ultimately we are getting 3 C2s for a simple alene molecule. Remember it, this is an important moiety. All of them contain several C2 axes, but those shown vertically pass through more than one atom. It is also to be noted that during the operations, one point in the molecule remains unchanged in space. Symmetry of this kind is called point symmetry to distinguish it from translational symmetry, which involves displacement in space. Okay. Now we are going to deal with plane of symmetry. Now it is a mere mirror. Okay, this is simply a mirror. So remember, a plane of symmetry is a plane which divides a molecule into two halves which are mirror images of each other. In other words, the reflection of two halves of the molecules across a plane gives a structure indistinguishable from the original. The plane is called sigma plane and the operation is sigma operation. Now remember, there is a plane within the molecule. This word is important. It will be inside the molecule, which will divide the molecule into two halves, and this is known as sigma plane. There are two kinds of sigma operations, one equivalent to the identity operation since they turn the molecule into the original ones. It is important to note that two halves themselves may not be superposable, and the molecule of water here we can see. See here, one is present, the plane itself. The plane in which the molecule is present is itself a mirror to divide the water molecule, whereas another plane passes through this oxygen and divides this one to give two equal halves. So two mutually perpendicular sigma planes are present. Now for the chloroform, we can see 3 sigma V's. Sigma V's means passing through the principal axis. We know here there is a C3 axis. Now if we consider planes, then one plane will pass through this Cl and in between these two Cls. Okay. Another plane similarly will pass from this through this and in between these two Cls. Similarly, another one will pass through this Cl and in between this Cl and this Cl. So it will be somewhat like this. So 3 sigma V's, each containing HCCl bond. Okay. So this one will be in plane with this sigma. Next we are going to consider for benzene. Now if you consider here, then this benzene ring has 1 sigma H in the molecular plane. So since it is perpendicular to the C6 axis, which is the principal axis, so it is 1 sigma H, whereas 6 sigma V's are present, same position as that of the C2 axis, which we have seen previously. So 3 passing through the opposite atoms and 3 passing through the opposite bonds. And for cis 1,3-dimethyl cyclobutane, see here there is a reflection. If seen from here, this hydrogen comes here. And similarly, if we consider this mirror, this methyl and this methyl shows a mirror image. So 2 sigma V's. Similarly for trans 1, there is 1 sigma V, hydrogen and hydrogen showing that. Now next one is our trans-dichloroethylene. So here what happens, the molecular plane that is coincident with the mirror plane, that is 1 sigma H, and we know that the axis of rotation is perpendicular to it, so here we get sigma H, not sigma V. So remember, when rotational axis, that is CN axis, is perpendicular to sigma, then that is sigma H, whereas when CN is in plane with sigma principal axis, then it is sigma V. Okay, now for cyclopropane we are getting 1 sigma H, that is passing through the plane, and 3 sigma V's. And for this moiety, that is ethylene moiety, we are getting 1 sigma H and infinite sigma H passing through internuclear axis. For naphthalene, we will get 2 sigma V and 1 sigma H. Try it on your own self and match it. Okay. And next, for ethylene, we will get 2 sigma V and 1 sigma H. Now again we will see for alene what will be the sigmas present. So this is our alene. Similarly, this is the HC, this is the HD, this is HA, and this is HB. Now here there are 2 sigma D, that is bisecting the C2s. Here is one in this plane and another is in this plane. How can we understand it? If we draw again the Newman projection, just like previous one, then it looks like this. A plane passing through these two will bisect this and this, whereas another plane passing through this two will bisect this and this. So 2 sigma D. Now remember, sigma planes and CN axes often occur together, and since a convention has been set up by placing the principal axis vertically, the sigma planes may be designated in relation to it. Sigma plane containing principal axis as sigma V, and sigma H represents plane perpendicular to the principal axis and unit. Sigma D represents a plane bisecting the angle between two C2 axes. Remember it. 3 types of planes we obtained. The number of sigma V and sigma D planes may be and usually is greater than 1. Now, the third one we are going to deal with is center of symmetry. A center of symmetry or an inversion center is a point within a molecule such that if an atom or point is joined to it, encounters an equivalent atom. In other words, inversion of all atoms in the molecule through the point gives an arrangement indistinguishable from the original one. Simply speaking, if we see the example, here is a point and here is the point. So if we join it, we will get, on going same distance, same substituent. Similarly for this one, here is the point, here is the point. If we go from here, this will be same distance, and going from here, this will be same distance. So here there is one I, here also one I. Similarly for this one, if we go from this distance to here, we will get OH. Same distance traveled gives us OH. So here also one I. In truxylic acid, we will get same thing here, going from here CO2H. Here also CO2H. Here is pH and here is pH. So in the presence or absence of an inversion center in any molecule can be easily ascertained by an inspection of the molecule. Okay, so it is easy to obtain. This is the easiest one. Next, the last one, which is the toughest one, is the improper axis of rotation, or improper or alternating or rotation reflection axis. In this one, that is an improper or an alternating axis of symmetry of order of n, is an n-fold axis such that a rotation of 360 degree by n around it, followed by a reflection in a plane perpendicular to the axis, generates a structure indistinguishable from original. The order of the two operations may be reversed without change in result. The vertical axis of alpha truxylic acid is a S2 axis, since a rotation of 180 degree around it leads to the structure, which on being reflected across the plane of the ring gives a structure superposable on the original. So what does it mean? Suppose you have this one. This is a circle. Okay, take a simple example. This is a circle and you rotate it by 180 degree. This is your first operation, rotation by any of the angles. Then you get back the same circle. But sometimes it may happen that here is a hydrogen, here is a hydrogen, and here also H. Okay. Next case, what happens? You are just reflecting it by a plane. So ultimately you get this kind of thing. See this one? This kind of thing. Here is a hydrogen, here is a hydrogen on being reflected. So this is known as S axis. Okay. If there were 4H here, here also 4H, then these two structures, first starting structure and the ending structure, this one and this one, would have been same. So we are going to have an S 180 degree axis. So S 180 degree we don't write, we write SN axis. So it is S2 axis. This is the operation. Basically it means first rotate and then reflect. So we will see the example and then we will understand it easily. So see here, this is the trioxylic acid. So see here, conformation. Next example is that conformation of mesotartaric acid on being similarly rotated and reflected. We can see that superposable structures are being obtained. So see this example. Similarly from here, rotation and reflection. So ultimately same structure will be given. First here rotation is done, then reflection. So the SN axis is called alternating axis of symmetry because the equivalent atoms or groups exchange by an operation and alternately above and below the reflection plane. Now it may be observed that an S2 operation brings about the exchange of like pairs of atoms or groups which are equidistant but in opposite direction from a center, and that is their coordinates change from x, y, z to minus x, minus y and minus z. So S2 axis is equivalent when inversion center, as I have told you here in this example. Now S1 operation consists of C1 and sigma. So remember, since C1 operation leaves the molecule unchanged, so S1 operation is equated as sigma operation. Okay, the plane are not the same though the operations are. Therefore, instead of looking for S1 and S2 axis in a molecule, one should look for sigma plane and an inversion center. There are few known molecules which do not have a sigma plane or an inversion center, but they have SN axis, and the example of such a moiety is 3,4,3-4- tetramethyl spiro 1-1 dipyrrolidinium ion, and we will see this one. See here it possesses a 90 degree axis. So first there is a rotation by 90 degree and then a reflection through this plane present within the body. Okay, we are considering the plane within. So ultimately we will get the same structure back. So this was our last example for inversion center. So this much for today. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.